Good morning everyone, I'm Taning from University Technology Malaysia and I'll be presenting my final project which title is Simulation of Electrical Circuit of Multi-Layer Capacitors for Energy Storage Application, and my supervisor is Dr. Mastura Shafinas. This is my presentation outline. So first I will go into introduction first. So MLC, also known as supercapacitors or multi-layer ceramic capacitors, and actually function as an essential energy storage device for high frequency circuits and power system because it has high volumetric efficiency, scalability, and also exceptional reliability. And the figure 1.1 here shown is a cross-section view of an N-layer MLC. So going to problem background, we're talking about the limitation of traditional lump RLC models. So for traditional model, they fail to capture the distributed and frequency dependent behavior of MLC, also provide inaccurate prediction for high impedance under high frequency conditions and transient response during rapid switching, and they will neglect equivalent series resistance and equivalent series inductance. So this comes for need for advanced model which the lossy transmission line models address distributed effects and frequency dependent losses. Next, going to the problem statement. Firstly, advanced transmission line models have difficulty scaling to wider geometries, making it hard to predict how capacitance and impedance behave when the geometry changes. Secondly, most studies focus only on fixed capacitance value or specific size, which will limit the understanding of time domain response across varied geometries. Thirdly, there is a gap in studies that examine how material properties like band gap or dielectric constant will impact the MLC performance. So to address this issue, we come to three objectives, which first is to determine the mathematical relationship geometry of MLC structure towards total impedance. Secondly is to analyze the time domain response for different scale multi-layer capacitors. And the third one is to observe the MLC performance using device structure simulation. And this will be my literature review. So going to the methodology, this is my flowchart. So the flowchart actually combining three parts of the objective, including the mathematical relationship part, the time domain response, and also device structure simulation. So for the first part is the mathematical relationship. So I will need to explore how the changes in MLC geometry affect the capacitance and characteristic impedance using following equation from the relevant research paper. So I actually generate the data using varying width from 1mm to 10mm using Excel, and I plotted the graph for the capacitance versus width and also impedance versus width. Then going to time domain analysis, I will model the transient response of MLC under discharging condition. So the figure 3.1 here shown is the proposed transmission line model. I am modeling this circuit using the table here. The table shown is the parameter used when I'm modeling this transmission line models. Then after that, I will generate the graph using the load resistor to see the voltage versus time to show the discharging conditions. Focusing on validation model structure act like a capacitor. So the figure 3.2 here shows the one layer capacitor structure with contact definition. Material used here is for electrodes is copper, the substrate used is SiO2, and the dielectric used is silicon doped with n-type concentration of 1 × 10^16. Then the process applied will be like layer deposition and the doping and activate it, and also do the contact definition using the ohmic type for electrode left and right. Then the scan type used including 3 types from the figure 3.3 here. So we are actually using the equilibrium scan, the voltage bias scan from 1 volt to -1 volt, and also time dependent scan. And going to phase 2, focusing on multi-layer configuration and dielectric comparison. So for figure 3.4 here is the 3-layer MLC structure when the dielectric used is silicon, and the yellow box shown here is the 1 layer which the overlap area is fixed parameter using 6 micrometer times stack 6 micrometer. And the dielectric materials, I will use 3 types, which is silicon, 4H silicon carbide, and also germanium. Then going to result and discussion. So first is the mathematical relationship part. This is the graph generated. Then the key relationship here is that impedance is inversely proportional to the width, and capacitance increase proportionally with the width. So it actually provide insight for optimizing the MLC geometry for specific performance metrics, and it validates the mathematical relationships derived earlier. Then going to the time domain analysis, I start with the width equal to 5.3mm first. This is the setup, and I'll compare it with the experimental data as a validation. And the transient response observation here demonstrate the step response behavior with gradual voltage decay due to the inductive and capacitive element. And this will be my result. So I actually simulate the distributed and transient nature of MLC, and I also ensure the model capture real world frequency dependent losses Then you can see here there is a minor oscillation observed due to the interaction of inductive and capacitive element, but the overall behavior aligns closely with the experimental data, and I validate the improved model. Then I'm going to vary with which is 1 millimeter to 10 millimeter, and this will be my result. So you can see here when the MLC going narrower, it discharge faster but exhibit larger voltage oscillation. Like example, you can see here when 1 millimeter until 3 millimeter, the oscillation is too large, so actually it cannot function well as a capacitor. So actually we can choose more than 3 millimeter, like 4 millimeters start here. So and also when the MLC going wider, it will discharge more slowly and show a damped oscillation, so demonstrating higher capacitance and better energy retention. And going to the device structure simulation, so first we can see from the figure 4.1, which is the band diagram. So actually they provide a flat profile across the dielectric, so indicates no internal electric field under equilibrium. So it confirms the structure act like a capacitor, not a diode or transistor. Then the figure 4.2 shown is an electron concentration diagram. So there is a slight drop near the electrodes and high electron density in the dielectric center. Then going to the potential distribution shown in figure 4.3, so you can see the highest potential is shown at the dielectric center and near the electrodes. So actually provide a stable internal field with no contact dominance. And also figure 4.4 shown here is the differential potential diagram. Then going to the phase 2, first we were talking about the electric field distribution across the dielectric. So first is for silicon. You can see here from silicon, the peak field is around 7.67 times 10 power 6, which actually silicon provide efficient charge separation and stable field formation. And going to 4H silicon carbide, the peak field is highest among three material, which is around 8.94 times 10 power 6. So it actually have an excellent high voltage tolerance and field control. And for germanium, it has lowest peak field is around 6.7 times 10 power 6. So the weaker field is actually due to germanium high polarization and low breakdown tolerance. Next, going to the electron current characteristics under the bias. So for all the three materials, there is nearly zero across all dielectric regions, as shown in figure 4.8. So it actually confirms there is a capacitive-like behavior because no conduction between the electrode left and right through the dielectric. Then going to the time-dependent discharging behavior, for silicon, the graph shape is like a smooth downward curve, so it actually provides stable and controlled discharge. So silicon is more suitable for reliable or gradual energy release. Then for 4H silicon carbide, the graph shape is like an inverted L curve. So this material actually have a fast initial discharge, then it will hold the charge. So it actually ideal for retaining charge post initial response. And for germanium, the graph shape is like a C-shaped curve. So actually it has high initial current and a prolonged discharge. It is more prone to steady leakage and prolonged energy release. So for device structure simulation, the conclusion is that the silicon has a best balance between the discharge control and retention. And for 4H silicon carbide, it has a quick discharge but may permit more special current spread. And for germanium, it confined flow, but it will have slower or prolonged discharge. So in conclusion, for my final project, I have do the model development which the transmission line model for MLC successfully developed and validated. In terms of geometry impact, when the wider capacitors exist, it has increased the capacitance and decreased in impedance. Then for time domain finding, narrow MLC will have fast discharge, more oscillation, but for wider MLC, it has slower and stable discharge. Going to material behavior, I will be explaining in last slide. So all the performance actually linked to the bandgap and carrier mobility of each of the material. So in future work, we can do the advanced layer structure, which we can simulate beyond 3 layers to explore more field dynamics and energy stacking, and we can use also more dielectric material with varied thermal or electrical properties. And also we can do the simulation refinement, which we can improve the mesh size, the contact area, and introduce temperature effects, and also do the experimental validation by doing the lab-based testing of fabricated MLC. And this is my reference. Thank you.